Okay. Hello students, welcome back in the lecture series of machine learning. Now today's topic is inductive bias. So let's see what's inside the inductive bias. So introduction to inductive bias. Inductive bias refers to the assumption that learning algorithm makes too generalized from limited training data set to for unseen data. That's a slightly grammatical mistake. Anyway, so that means suppose that you are applying an algo or method technique. Okay, let's say of a machine learning. Okay, now that depends upon data set. So we want that this algo machine learning technique which you have applied on this data set should be generalized so that it can cater the unforeseen data. So that is why the inductive bias is used. So in machine learning the models learn from finite data set, okay, and must predict accurately on new and unseen example. The inductive bias of the model guides how it learns patterns and makes predictions beyond what it has explicitly seen. So suppose that you do training and then testing on a given data set. Okay, it is a possibility that this particular data set may not have certain record. Okay, so if that records comes back to your model, then for that model it is totally unforeseen data, and in that condition the model should accurately predict the outcome. So that is what our goal is. So why inductive bias is important? Without inductive bias the model has infinite possible hypotheses, correct? So we always have infinite hypothesis space. So it helps generalize well to unseen data. A strong bias can improve the learning speed but may lead to underfitting. If your data size is small, so you can learn up, your time for taking for learning may be very less, but you are prone to underfitting. A weak bias allows the flexibility, that means you can generalize, but it leads to, means you be very specific, so you can be doing overfitting. So these are the problems associated with all the machine learning techniques. So over there the inductive bias comes to rescue. Okay, now understanding the inductive bias in machine learning, a machine learning model must make assumptions to choose the best hypothesis from many possible ones. So we know that machine learning encounters a lot of hypotheses and we have to choose the best depending upon the data. So these assumptions are inductive bias of model. So this justifies the name. So suppose that we have three data points 1, 2, 2, 4, 3, 6, and we want to predict f of 4. So the possible hypothesis can be, we can have, means the model in which in the hypothesis space you can have a linear function like f equals to 2x, because you should see the relation, the model will see the relationship. Input is 1, output is 2. Input is 2 and output is 4. Input is 3 and output is 6. So at this point you can have 2 times 4, that becomes 16. So model can see this. It is just twice of your input. Whereas it can be a polynomial function also, because okay, so that means over here we can have some function like fx, okay, some degree of some power, let's say with the coefficient b naught plus, okay, let me So fx equals to b naught plus, let's say, b1x plus b2x square or something like that. So we can have a polynomial function, okay, where f equals to 16, and we can have a random function, okay, fx equals to 10, because this relationship may break when the new inputs start coming. So if the data set is just limited to this, it is perfectly okay to guess that it is twice the input is twice the output. But which model we should choose? Suppose we have the model as may learn the linear function, polynomial or random. So model can choose anyone. So how we assume? So we assume the linearity, we predict 2fx. If we assume non-linearity, we will choose this one, and okay, so or some higher order of polynomial. Okay. So that means inductive bias determines the which hypothesis is preferred. So that is why the term bias is there. Because under the constraints of limited time computation power, it is not possible to explore all kinds of hypotheses for a given data set and then find that this one is the best. So you have to be biased at that point, that okay, the model reflects this kind of relationship between input and output or the targets, then this kind of relationship or the hypothesis must be taken into consideration. So what are the types of hypothesis learning? So we can have mostly, yeah. So types of hypothesis learning. First we have a language bias, hypothesis space restriction. So it restricts the form of hypothesis that the model considers. You put a constraint on. Example, the decision tree assumes the solution can be represented as hierarchical decisions. Okay. So this is known as language bias. The preference bias, search strategy bias. The model assigns a higher preference to the certain hypothesis over others. Example, linear regression prefers the linear relationship even if the data fits as polynomial. Or we can have an algorithm specific bias. So different learning algorithms have different inductive bias. For example, a neural network assumes a smooth continuous function. Naive bias can assume the feature independence. Okay. So, and k nearest neighbor assumes the nearby points have similar labels. So these are what? These are assumptions. So that is known as inductive bias. Okay. So where we can use the inductive bias? So we'll take first, as we have discussed in the previous slide, the decision tree. Assume the data can be split into hierarchies. Okay. Bias prefers shorter trees. Neural networks assume data follows a smooth function. There are no zigzags. So bias prefers the distributed representation, feature abstraction. K nearest number assumes that all the nearby points have the same label or they belong to same class. So the bias is locality based decision. In support vector machine, SVMs, assume the data is linearly separable in feature space. Bias prefers the maximum margin classifier. The Bayesian learning assumes the prior knowledge can improve the learning, so that we have a priorities over there. So bias preferred high probabilistic reasoning. Okay, inductive bias versus overfitting and underfitting. So inductive bias plays a crucial role in balancing the bias variance trade-off. Okay. So strong bias, we have that is, for example, in linear regression, faster learning, fewer data points are needed. The potential problem is underfitting. Okay. May miss the complex pattern. If we go for a weak bias like deep neural networks, The flexible learning fits complex functions, but the overfitting, that is, it can memorize the noise also. A good bias should balance flexibility and challenge. So it is up to the person who is applying how the balance is actually maintained. Okay. So bias variance trade-off has to be taken. So no free lunch theorem and inductive bias. So no free lunch theorem states that no single learning algorithm is best for all problems. It's obvious that particular kinds of algorithm or a model prefers certain kinds of data. Okay, so if that data is according to that model, then in that case that model outperforms the other models. Okay, so this means a strong inductive bias works well for some tasks but fails for other. Choosing the right inductive bias depends on the feature of problem. Okay, so it depends on the feature of problem. For example, linear regression works well if the true function is linear. Dysentery, if we have a rule based or hierarchies are there. Okay. So practical implication of inductive bias: choosing the right model. If the data has a linear relationship, use linear SVM, a linear regression or SVM. If the data has a complex hierarchical patterns, use decision trees. Feature engineering: if you are using naive bias, okay, ensure the features are independent. If you are using neural network that provide enough data to avoid overfitting. And for L1 and L2 regularization, in the neural network model modifies the inductive bias to prefer simpler model. Dropout in deep learning helps reduce overfitting. So in the conclusion is, the inductive bias is a fundamental concept in machine learning that guides how algorithm generalizes from training data. It helps choose meaningful hypothesis. Okay, but too strong or too weak a bias can lead to underfitting or overfitting. Simply say one of the most fundamental problems, or whatever, whenever you encounter, you make a model, people will ask what is the how much it is overfitted or underfitted. So the key takeaway lessons are: inductive bias is necessary for generalization. Different models have different biases. Choosing the right bias is a problem dependent, and a good bias balance accuracy and flexibility. Thank you, students. That's all in the inductive bias.